Hello, this is Mr. Dooley, and I'm going to get you going on Chapter 11 here. This is a lesson that will cover the first two sections of Chapter 11, which is about sequences. So we're going to start off with a couple of definitions of a sequence. First, the Webster Dictionary definition: set of elements ordered, such as the natural numbers. Natural numbers, if you remember from probably the first or second day of school, the natural numbers are also known as the counting numbers. So they actually reference the natural numbers as a sequence in Webster's dictionary. Our math textbook, it says it's a function whose domain is the set of natural numbers. It's interesting that we use natural numbers twice here, which is called the term number, and whose range is the set of term values. So let's take a look at some very popular examples of sequences. First off, this is called the Fibonacci sequence. And you can see, if you look closely at this Fibonacci sequence, the term here, 2, is the sum of these two terms, right? So plus 1 is 2. And if you keep going, the 3 here is the sum of the previous 2. 1 plus 2 is 3. And the 5 is the sum of 2 plus 3. And this is called Fibonacci's sequence, the Fibonacci sequence. Very, very famous. The triangular numbers, that's also a famous sequence. The way that a triangular numbers works is if you make triangles out of dots, those would be the triangular numbers. So this is 1, this is 3 dots, this is 6 dots, this is 10 dots, and that represents the triangular numbers. If you look closely, you're just adding one more, right? So that's plus 2, that's plus 3, that's plus 4, plus 5, etc. And number 3 and 4, number 3, very simple, the multiples of 5. Multiples of 5. So you could see that as you move to each term, you are constantly, remember that word, constantly adding 5. And lastly, the powers of 2, you are constantly multiplying by 2. Once you figure out the pattern of a sequence, you can very, very easily write out the next few terms. You could write out terms to infinity if you wanted to, but once you know once you figure out the sequence, writing terms is not very challenging. It's a very easy thing to do. Now, what I would like you to do is to find the 10th term, and notice we abbreviate that T with a little subscript 10. Find the 10th term for each of these. So just pause the video, take a moment, and find the 10th term of each of these sequences, and then when you come back, you'll see the answers. So here you go. The 10th term in both 1 and 2, coincidentally, are both 55. The 10th term in number 3 is 50, and the 10th term in number 4 is 1024. Okay, so we are going to look very closely at the last two sequences, sequences 3 and 4, in this chapter. Sequence number 3 is called an arithmetic sequence. There it is right there, an arithmetic sequence. It's a sequence in which one term equals a constant added to the preceded term, excuse me. There's that word constant that I was mentioning earlier, and that word constant in this case, since this arithmetic sequence down here, the constant that we would be adding each time would be 3. It's pretty obvious to see that it would be adding 3 each time. 13 is the first term, 16 is the second term, 19 is the third term, 22 is the fourth term. So an arithmetic sequence is where you are adding a constant to each term. Constant meaning doesn't change, don't change it. You see, in the first two examples, the triangular numbers and Fibonacci, you are constantly adding, but you're adding a different value each time. When you add the same value, that's what is called a constant. And so in this problem, it says find the 58th term. Now, if we were going to do this problem using brute force, what we would do is we would write out until we got to the 58th term, right? And so we would just continue this pattern of adding 3, but you could see that this would get old very quick, old and tired very quick. And we would have to count it all the way out to the 58th term. Now, is there a better way of doing this? Well, absolutely there is. What I want you to do is I want you to just take a moment and see if you can figure out what the 58th term will be. I'll pause the video and then see, or you pause the video and then see if you could figure out what that 58th term is. And then when you come back, I'll show you how to do it. All right, so here's the mathematical way of doing this. Well, brute force is mathematical, but this is the way that we would prefer to do it, the more economical way of doing this problem, efficient way. So if you notice, we're always adding 3, right? Actually, you know what? Let me do this in red so you can see it. We're always adding 3, right? And so, for example, let's take this. Let's take a look at that term. This is the 5th term, right? That's the 5th term. How many 3's did I add to get to the 5th term? Well, 1, 2, 3, 4. I only added 4 3's. So if you think about that, to get to the 58th term, I'm going to take that 13 and I'm going to add to it 57 3's. 3's is my constant that keeps getting added, and I would add 57 3's to get to the 58th term. See that? I'd add 57 3's to get to the 58th term. So 57 times 3 is 171. We add 13 to it, and we get 184. So the 58th term in this sequence is 184. Now, what I've done here is actually using a formula. And that is on the next page of your notes. And there it is right there. That's to find the nth term in arithmetic sequence. And each of these symbols here has a definition. So Tn is the nth term. T1 is my first term. D, this is what we call the common difference. That's exactly what we are adding. It's you could also think of it as the adding constant. In this case, it was 3. And then we times it by n. N is the number of terms. And then the n minus 1, I explained earlier, is because we want to add 1 less of the number of terms. So this formula that we did, right, to find that 58th term, right, n was 58. And so we took the first term, which was 13. There's that. There's that. And what did we add? We add the common difference was 3 times 58 minus 1, which was 57. So everything is there. It's all there from the formula, from the work we had done earlier. Okay? All right. Now, sequence number 4, that's called the geometric sequence. So we have two different kinds of sequences. I forgot to bold this, so if you want to take your pen and underline that or bold it or highlight it or whatever, but the geometric sequence is our second type of sequence that we're going to be studying. So we have arithmetic sequence and a geometric sequence. And the geometric sequence is where you're multiplying. So arithmetic we add, geometric we multiply. And so here's a good example. Find the 12th term of the following sequence. So we take a look at this sequence, and hopefully you could see that as we go from one term to the next, we are timesing by 3. 1/9 times 3 is 1/3. 1/3 times 3 is 1. 1 times 3 is 3. And so this is an example of a geometric sequence. Now, to find the 12th term, 12 is not that cumbersome. 12 is not that big of a deal to just kind of grind out. So like, the 5th term, T5, would be 3 times 3, which is 9. And you could probably just grind this out, especially on your calculator. You could grind this out. 9 times 3 is 27, and 81, and blah, 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 blah. So it really wouldn't be a problem to grind out. And if you went all the way to the end, the 12th term would be 19,683. Now, is there a formula for this? Of course there is. There is a formula for this. And here it is right here on the bottom of the page. And it has a similar feel to the arithmetic because there are some things that pop up that are the same. For example, Tn, right? The nth term. T1, we always start with the first term. Here's the difference, though. In a geometric sequence, we use the letter R. And what we call that the common ratio. In other words, it's what you're multiplying by. In our previous example, it was 3, so R would be equal to 3. And notice, we still have the n minus 1. So the n minus 1 is a popular thing in these sequences. And so if we were to use the formula to do this particular problem, to find the 12th term, we start with the first term, which is 1/9, and we times it by my common ratio, which is 3, to the 12 minus 1 power. All right, so what is that? 1/9 times, let's see, 3 to the 11th is 177,147. Times that by 1/9, and you get your 19,683. So these formulas are big time. And if we were in a situation where we were in school, we would have you memorize them. Luckily, you don't have to memorize them now since we're not in school and you have access to your notes and stuff. But they're actually not hard to memorize if you really had to, because they are kind of built using some common sense. All right. Let's turn to the next page, page 3, and we got a bunch of examples to do. So there's 8 examples here. I'm just going to do a few of them, and then you could do the rest on your own. But this just says determine whether the sequence can be arithmetic, geometric, or neither. So there's just 3 options. If it's arithmetic, find the common difference. If it's geometric, find the common ratio. If it's neither, see if you could come up with a formula for finding the nth term. So let's just jump around. Let's pick a few that are pretty good. Let's do number 4. Number 4 kind of jumps out at me. You got 25 to 50, 50 to 75. Well, I think that's pretty clear that you are adding 25 each time, and so that would be arithmetic, and your common difference would be 25. Right below it, 1/2, 1/3, 1/4. Well, that's not arithmetic, because if it was arithmetic, each of those changes would be constant. And to go from 1/2 to 1/3, you would be minusing 1/6. And that is not the case to going from 1/3 to 1/4. You're not minusing 1/6. So it's not arithmetic. So you're just kind of ruling that out. Is it possibly geometric? Well, if it was geometric, then we would be multiplying by the same value. And so 1/2 times what is 1/3, right? 1/2 times what is 1/3? Well, 1/2 times 2/3. 1/2 times 2/3 is 1/3. So is 1/3 times 2/3 1/4? Is this true? No, it's not. It's 2/9. So this is not geometric either. So this is an example of a sequence that would be neither arithmetic nor geometric. Okay? And lastly, we got to do one that's geometric. Here's one that's geometric, number 5. All right. Now, why is this geometric? Well, what are you multiplying by to get from 2 to -4? You're timesing by -2, right? And then you times -4 by -2, and you get 8, positive 8. So my common ratio is -2, and this is certainly geometric. All right, I'm going to pause, or you pause it here, and I'll write out the answers for the other ones. You could try them out. All right, so there you go. I did ask in the instructions for finding the nth term for things that are neither, kind of come up with a formula. So for example, number 8, what I'm looking for is something like the nth term in this would be, it looks like n plus 1 root of 5, right? So this, right, because this is the first term, and that's a square root. That's the second term, that's a cube root. This is the third term, that's the fourth root. So you take the term number and you add 1 and take that root of 5. So that's kind of what I was talking about in coming up with the nth term. All right, last page are a bunch of examples as well, 4 more examples. So I'm going to do a couple of them and leave the others for you to do, to practice. Let's take a look at number 9. Number 9 says, given the geometric sequence, now that's key here, that they actually tell us that it's a geometric sequence. So they say it's a geometric sequence, and they want to know, okay, what term is that? That 34,816, what term is that? All right, so since it's geometric, we know that we can use this formula. And we know some of these things. Like, for example, this is T1. So I know this would be 17. I know the nth term. This is the nth term right here. 34,816. I actually know my ratio. I could figure out the ratio because they've told us it's a geometric sequence. So how do you get from 17 to 34 using multiplication? Very simple. You multiply by 2. So the ratio is 2. N is what we're looking for, right? We're looking for what numbered term is that? Is this 3416? So this is an algebraic equation. So what we're going to do first is we're going to divide by 17, which gives us 2048. And when you get it to here, you could either use logs, or if you are up to date on your powers, 2048 is 2 to the 11th. And so then n minus 1 would equal 11. So n would equal 12. So it would be the 12th term, right? If you did not recognize that 2048 was a power of 2, you can use logs, take the log of both sides, and do it that way. But when you do these problems, most of the time you're going to recognize the values. All right, so why don't you guys try number 10. I'll pause it here and try number 10, and when you finish, I'll have the answer written down, worked out. All right, let's do 11 together, and then I'll let you guys do 12, and then the lesson will be over. So in number 11, they don't tell us whether or not it's a geometric or arithmetic sequence, but you should be able to tell pretty quickly that it is geometric. Now, why is it geometric? Well, because if you look at how you are moving from one term to the next, you should be able to tell that you are timesing it by -5, right? 1 over 25 times -5 would be -1/5, and then if you times that by -5, you would get +1. Now, it says what term number is the last term shown? So we're going to do the same thing we did previously. We're going to use that formula for finding terms for a geometric sequence, now that we know that this is geometric. And so we know that our nth term is negative, wow, that's a big number, 1,953,125, and it's negative. And the first term is 1/25 times -5 to the n minus 1. Now, the negative thing is going to be an issue, but I'll show you how to kind of deal with that here. So first times by 25, and so this is going to be even a bigger number here. And you get -4,882,8,125 equals -5 to the n minus 1 power. Now, if you were going to try and do logs here, it wouldn't work because you'd be taking logs of negatives. So my advice to you is just cancel out the negatives. You know, looking back at our original sequence, if our ratio is -5, every other term will be negative. So like term 1 was positive, term 2 is negative, term 3 is positive, term 4 would be negative. So we do know that this has to be an even numbered term, right? Since it's negative. So my advice would be just cancel out the negatives, and then you can take the logs. You could do a log, right? So this is the log base 5 of 48,828,125 equals n minus 1. I'm just converting from exponential form, this is exponential form, into log form. Use your calculator to find the log of that, was that 48 million? Yeah, some 48 million. And you get 11. 11 equals n minus 1, n equals 12. And so it's the 12th term. All right. You guys can try the last one and pause and come back and you'll see the answer, and then the lesson's over. Dopey me, didn't even realize that it was the same problem as number 10, just written in the reverse order. But anyway, n equals 37. So exit slip should be posted, and good luck.